Welcome everyone. In this lesson, we will explore how to tackle systems of nonlinear simultaneous equations using a powerful numerical tool from the SciPy library called FrySolve. Often in science and engineering, we encounter equations that are too complex to solve by hand, and that is where methods like these become invaluable. Our main goal today is to understand how to set up these problems for a numerical solver and interpret the results. We will start with a specific example, finding x0 and x1 that satisfy two conditions simultaneously. First, x0 multiplied by the cosine of x1 equals 4, and second, x0 multiplied by x1 minus x1 equals 5. To use FrySolve, we first need to rewrite these equations so that they equal 0. So we will define a first function, let us call it f1, as x0 times cosine of x1 minus 4, and a second function, f2, as x0 times x1 minus 5. The FrySolve tool then works by trying to find the values of x0 and x1 that make both f1 and f2 simultaneously 0. We will learn how to package these functions and provide an initial guess to kickstart the search for a solution. By the end, you will be equipped to solve similar systems you might encounter in your studies or future work. Now let us look at how we translate this setup into Python code. We begin by importing the FrySolve function from scipy.optimize and the NumPy library, which is helpful for numerical operations like cosine. We define three functions. The first function, named f1, takes a list or array x as input, where the first element is our x0 and the second is x1. It then calculates x0 times numpy.cosine of x1 minus 4. Similarly, the second function, f2, also takes this x array and calculates x0 times x1 minus 5. A third function, which we can call f, is defined to return the results of both f1 and f2 as a pair. This is the function that FrySolve will work with. We then provide an initial guess for x0 and x1, for instance 0 and 1 respectively, bundled into a list. When we call FrySolve with our combined function f and this initial guess, it computes the roots. The output shows these roots are approximately 6.5041 for x0 and 0.9084 for x1. If we substitute these root values back into our original functions, f1 and f2, we find that the results are extremely close to 0, something like minus 6.4 times 10 to the power of minus 11, and 1.16 times 10 to the power of minus 10. This confirms that FrySolve has successfully found a valid solution. Let us consider another example to solidify our understanding. This time, we are tasked with solving a system involving exponential and logarithmic functions. The equations are e to the power of x equals the natural logarithm of y, and the natural logarithm of x equals e to the power of minus y. Just as before, we need to rearrange these so they are in the form where the function equals 0. So, our first function, f1, will calculate e to the power of x minus the natural logarithm of y. Our second function, f2, will calculate the natural logarithm of x minus e to the power of minus y. The Python code mirrors the structure we saw previously. We import necessary tools, including FrySolve. We define f1 that takes an array, unpacks x and y, and returns the expression for the first rearranged equation. We do the same for f2 with the second rearranged equation. Then, a main function f is created to return the outputs of f1 and f2. We supply an initial guess, for example, x equals 1 and y equals 1. Calling FrySolve with this setup gives us the roots for x and y. The code then prints these root values and also evaluates our function f at these roots. which should again yield values very close to 0, confirming the solution. Our next problem involves a bit of geometry. We are asked to solve a system of two simultaneous equations. First, 2 times x squared plus y squared equals 1, and second, the quantity 0.5 times x minus 0.5 all squared plus 2 times the quantity y minus 0.25 all squared equals 1. These two equations actually describe two different ellipses on an xy plane. As you can imagine, two ellipses can intersect at multiple points. In this particular case, because these are quadratic equations, there can be up to 4 distinct intersection points, meaning 4 pairs of x and y values that satisfy both equations simultaneously. The task for our numerical solver will be to find the coordinates of these intersections. The code we will see next is set up to find one such intersection point, depending on the initial guess we provide. Understanding the geometric nature of the problem can often provide insight into the number and nature of solutions we expect. To find an intersection point for the two ellipses, we once again set up our functions for FrySolve. The first function, let us call it f1, will take an array containing x and y. It calculates 2 times x squared plus y squared minus 1, which is our first ellipse equation rearranged to equal 0. The second function, f2, similarly takes the x and y array and computes the expression for the second ellipse. The quantity 0.5 times x minus 0.5 squared plus 2 times the quantity y minus 0.25 squared minus 1. Our main function f then returns the results of f1 and f2. We provide an initial guess for x and y, for instance, x equals 1 and y equals 1. Passing our function f and this initial guess to solve, the solver will work to find a pair of x and y values that make both f1 and f2 0. The code then prints these root values, representing the coordinates of one intersection point, and also prints the values of our functions at these roots to verify they are indeed very close to 0. After finding an intersection point, it is often very instructive to visualize the problem. Our goal here is to plot both ellipses on the xy plane, show their intersection points, and also mark their centers. To plot an ellipse, we typically use its parametric form. A general ellipse, centered at h, k with semi-axes a and b, can be described by x of theta equals a times cosine of theta plus h, and y of theta equals b times sine of theta plus k, as theta varies from 0 to 2 pi. For our first ellipse, given by 2x squared plus y squared equals 1, we can rewrite this as x squared over the quantity 1/2 plus y squared over 1 equals 1. This tells us its center is at 0. Its semi-axis a is 1 over the square root of 2, and semi-axis b is 1. So, its parametric equations are x of theta equals cosine of theta divided by the square root of 2, and y of theta equals sine of theta. For the second ellipse, given by 0.5 x minus 0.5 all squared plus 2 times y minus 0.25 all squared equals 1, a bit of algebraic rearrangement shows it can be written as x minus 1 all squared divided by 4 plus y minus 1/4 all squared divided by 1/2 equals 1. This means its center is at 1/4, with semi-axis a equal to 2 and semi-axis b equal to 1 over the square root of 2. Its parametric forms are x of theta equals 2 times cosine of theta plus 1, and y of theta equals sine of theta divided by the square root of 2 plus 1/4. Finally, let us see how to generate the plot using Python. We use NumPy to create a range of theta values from 0 to 2 pi. We then define two functions, p1 and p2, each taking a theta value and returning the corresponding x and y coordinates based on the parametric equations we just derived for the first and second ellipses, respectively. For the second ellipse, its center from the parametric equations is at x equals 1 and y equals 0.25. Using these functions, we generate lists of x and y coordinates for many points along each ellipse. The code then uses matplotlib to plot these sets of points, effectively drawing both curves. It also marks the center of the first ellipse at the origin, and places a separate marker labeled O2 near the center of the second ellipse at coordinates x equals 1, y equals 0.35. Additionally, it plots the intersection point we found earlier using phi-solve. A legend and grid are added for clarity. In summary, today we have learned a practical method for solving systems of nonlinear simultaneous equations using the phi-solve function from SciPy. We saw how to properly define our equations as Python functions that return 0 at the solution, and the importance of providing an initial guess. We applied this technique to various examples, including algebraic and transcendental equations, and even visualized the solution in the context of intersecting ellipses by parameterizing their equations. This ability to numerically find solutions and then visualize them is a powerful combination for understanding and solving complex problems in many scientific and engineering fields.